Ever wonder why water treatment plants add certain chemicals to your drinking water? Adding phosphate ions might seem like a small step, but it plays a powerful role in blocking harmful metals like lead from reaching your tap. The science behind this safeguard lies in solubility and equilibrium. Let's explore how phosphate ions act as chemical protectors, keeping your water safe and clean. This is Real Chem. To understand how phosphate helps protect our water, we can look at it from two perspectives, qualitative and quantitative. Qualitatively, Le Chatelier's principle tells us that adding phosphate should reduce the amount of dissolved lead. But to truly understand the impact, we need to put numbers to it. Connecting these two approaches gives us a deeper insight into how chemical equilibrium works and why phosphate treatment is so effective. Metal pipes can gradually develop a protective layer of insoluble compounds on the inside. For example, when phosphate ions flow through a lead-containing pipe, they react with the lead to form a layer of lead phosphate that coats the interior. This protective layer plays a crucial role in preventing lead ions from leaching into the water we drink. But it's only protective if it stays in place and doesn't dissolve, releasing lead back into the water. Lead phosphate is sparingly soluble. Its KSP is about 10 to the minus 47. This means a small amount dissolves, leading to a small concentration of lead and phosphate ions in solution. So as water flows through the pipe, some of the lead and phosphate ions from the protective layer may dissolve and enter the water. If we want to keep the lead out of the water, what can we do? According to Le Chatelier's principle, adding phosphate shifts the equilibrium to the left, preventing lead from dissolving. That's why water treatment facilities add phosphate ions to keep lead locked away in the protective layer. But how significant is this effect? Let's compare two situations, one where the water in the pipe is pure and another where it is treated with 1 × 10 to the minus 6 molar phosphate. In pure water, the solubility of lead phosphate is 2 × 10 to the minus 10 molar. Since each mole of lead phosphate that dissolves produces 3 moles of lead ions and 2 moles of phosphate ions, their concentrations are 3 times and 2 times the solubility, respectively. These concentrations are governed by the solubility product constant, KSP, which ensures that this product of the ion concentrations always equals the KSP value. What about for treated water with 1 × 10 to the minus 6 molar phosphate? Because the ion product must always equal the KSP, an increase in phosphate concentration must be accompanied by a decrease in lead concentration. This is exactly what we predicted using Le Chatelier's principle. As more phosphate is added, the dissolution reaction shifts to the left, reducing the lead concentration. To put this into perspective, the concentration of lead ions in pure water may seem small, but it still exceeds the EPA's recommended limits. Treating the water with phosphate lowers the lead concentration, making the treated water much safer to drink. We call this the common ion effect because to treat the water, we add sodium phosphate, a soluble form of phosphate. The added salt and the lead phosphate have an ion in common, the phosphate ion. This shared ion is what gives the common ion effect its name. This isn't just smart chemistry, it's a critical safeguard that makes every sip of water safer for you to drink. Whenever we add extra ions to a system, we're not just tweaking the chemistry, we're taking control of it. By harnessing the common ion effect, we can shift equilibrium to trap harmful ions like lead in insoluble solids, preventing them from reaching our taps. It's a simple yet powerful strategy that helps protect public health on a massive scale.